Recall that the two-dimensional heat conduction equation was on this form, where we on the left side has the partial derivative of the temperature U with respect to the time t. If there is no variation of the temperature with respect to t, that it's constant with respect to time, that is when the partial derivative of u is with respect to t is equal to 0, then this equation turns into the so-called Laplace equation. So the Laplace equation looks like this. It's the second derivative of u with respect to x plus the second derivative of u with respect to y, and this should be equal to 0. If the domain where we are going to search for the solution is called R, it's some bounded open domain in R2, then we call the boundary of this domain, we called it, for example, C, but it's also often called del R. We have some unit normal vector defined on this boundary, and we are going to search for solutions in various cases. And in order to find unique solutions, we have to know something more about the conditions on the boundary here. One such condition is a Dirichlet condition. Dirichlet condition means that the temperature U is known at this boundary. So it's defined on the boundary, but it's unknown in the middle in the interior of the boundary. The other type of boundary condition is Neumann boundary condition. Then the normal derivative of U is known at the boundary. The normal derivative, if U is the temperature, then the normal derivative with respect to n equals the heat velocity. So the heat velocity is then defined on this boundary. So this is called Neumann condition. And mixed boundary condition is when U is defined on some part of the boundary, for example this red region, and the normal derivative un is defined on this green part of the boundary. So this is three types of boundary conditions which are rather important when we are talking about the Laplace equation.